We now start chapter 2 of linear algebra, which is on vector spaces. We now introduce the definition of a vector space over an arbitrary field f, and then we will see some examples, and you will see that there are examples of two kinds essentially. In fact, they are called finite dimensional and infinite dimensional vector spaces. We will not formally call them finite or infinite dimensional vector spaces when we define them or introduce them for the first time, but later on we will be able to make it precise after we introduce the concept of dimension and a few other things. Let us start with the definition of an abstract field, followed by definition of a vector space over an arbitrary field. So, to begin with, a binary operation on a non-empty set X is a function from x cross x to x. X cross x is nothing but the Cartesian product of x with itself. Since binary operation is a function, therefore, for every pair of x and y in X, the image which is denoted by x circle y is a well defined element in X. The usual addition and multiplication of integers, rational numbers, real numbers, complex numbers are definitely examples of binary operations on these sets. What we will see, especially for the rationals, the reals and the complex numbers, is that these binary operations of addition and multiplication give a very special structure, and that is what is called a field. One more example. Look at Rn, that means Cartesian product of R n copies, or Cn, that is the Cartesian product of Cn copies. So, their elements typically are the n tuples. If you remember, we will stick to this notation that elements of Rn or Cn will be written as column matrices instead of row matrices. This is just a matter of convention and convenience, and we can define alpha 1 to alpha n plus beta 1 to beta n as alpha 1 plus beta 1 etc. alpha n plus beta n. This is also a good binary operation, a very natural one on Rn respectively Cn. And this binary operation is what is popularly known as pointwise addition of n tuples. So, the reason why it is called pointwise addition is you can see that the first spots are being added, then the second spots are being added, and so on, the nth spots are being added. So, it is a pointwise operation on the tuples. This is a very natural binary operation on Rn respectively on Cn. We now come to the formal definition of a field. Let F be a non-empty set with two binary operations plus and dot called addition and multiplication on F. Now, what is interesting here is that we use the same notations for these binary operations as the usual multiplication or addition of Q, R, C, Z, etc. You can think of this binary operation as a kind of natural abstraction of the usual addition and multiplication of numbers. Now, this triplet F plus dot is called a field if F plus and F minus 0 dot are abelian groups and plus a dot are related by the following distributive property, that is x dot y plus z is equal to x dot y plus x dot z for every x, y, z in F. Now, a few comments are in order. So, what are abelian groups? That means these two structures F plus and F minus 0 dot, their plus and dot are binary operations, they are abelian or commutative, that is x plus y is equal to y plus x and also x dot y is equal to y dot x. They are associative, they have identity element with respect to each of these operations and they have inverses. And you may wonder why we have only one distributive property instead of a few more. We could have written something like y plus z dot x equal to y dot x plus z dot x, but that would be redundant because F minus 0 dot is an abelian group and therefore, that dot is a commutative operation. This shows that just one distributive property takes care of distributive property from the other side also. Now, a few notations. The additive identity of F plus would always be denoted by 0 and the multiplicative identity of F minus 0 dot would always be denoted by 1. So, just to summarize, F is a non-empty set, there are two binary operations and the structures F plus and F minus 0 dot are abelian groups and the binary operations are related by the distributive property which you can see in the center. So, this is what is called a field. Let us now see some natural examples. If you remember the contents of chapter 1, then we talked about systems of linear equations, where we indeed started with a field and the notation was F, and I also wrote that F you could take as Q, R or C or ZP. So, now we come back to these examples and see them in the light of this formal definition. This Q plus dot, R plus dot, C plus dot are examples of infinite fields. That means these sets are infinite sets and you have the natural addition and natural multiplication. And another example which is somewhat different is ZP plus dot. It is an example of a finite field where P is a prime number and plus and dot are the addition and multiplication of integers modulo P. So, let me quickly tell you what ZP is. It is the collection of integers modulo P. That means, when you see an integer n divided by P, then the possibilities for remainders would be 0, 1, 2 and so on up to P minus 1. Now, if you take the collection of remainders, there are P of them, and you can define the addition of these remainders, so to say, but you have to keep in mind that whenever you add it up and if it gets bigger than P, then you have to read it modulo P once again and bring it back to a number within 0 to P minus 1. For example, if P is, let us say 7, and if you take 5 plus 3, which becomes 8, but again we have to divide 8 by 7 and the remainder is 1. So, modulo 7, 5 plus 3 is 1. One more example. This is what we call Q adjoint root 2, that is the collection of all those real numbers which are of the form a plus b root 2, where a and b vary over the set of rational numbers. You can see that this is an infinite set. It has various elements. For example, root 2 is also an element in this set. If you take a is equal to 0 and b is equal to 1, 1 plus root 2 is also an element in this set. If you take a is equal to 1, b is equal to 1. Now, what is interesting here is that if you take the natural addition and natural multiplication given by these formulae, that is a plus b root 2 plus c plus d root 2 is a plus c plus b plus d root 2, and a plus b root 2 dot c plus d root 2 is ac plus 2bd plus ad plus bc root 2. Then it is not a very difficult task to prove that this is a field with respect to these two binary operations. That means q root 2 with respect to plus is an abelian group, q root 2 minus 0 with respect to dot is also an abelian group, and the distributive property connecting plus and dot holds. Now, we are in a position to define a vector space formally. Let V be a non-empty set with a binary operation plus. Suppose that V plus is an abelian group. Let F be a field. Now, the basic thing that we require to define the vector space structure is that a scalar multiplication, so called, which is a map from F cross V to V, and this is the usual notation lambda comma x. This tuple is going to lambda dot x. Now, the abelian group V plus is called a vector space over the field F if the following properties are satisfied, namely lambda dot x plus y is lambda dot x plus lambda dot y for all lambda in F and x y in V. Lambda plus mu dot x is lambda dot x plus mu dot x for all lambda mu in F and x in V. Lambda mu dot x is lambda dot mu dot x for all lambda mu in F and x in V, and 1 dot x is x in V. So, these lambda, mu, etc. are usually used for elements from the field which are called scalars, and x, y are usually used for elements from the vector space V, which are usually called vectors. And if you recall, then 0, 1 were the additive identity and the multiplicative identity of the field F, but here you have one more 0 which is written in boldface, and that is supposed to mean the additive identity of the vector space V. We will now talk about some natural examples of vector spaces, and we will discuss at least one theorem which sort of gives you better idea about the structure of vector spaces. You will see that in the list of examples that we would be talking about, there are essentially of two kinds. One would be examples which fall into the category of finite dimensional vector spaces, and the rest would be examples of infinite dimensional vector spaces. This we will be making more precise later on. We will see some examples of so-called function spaces, which will be discussed again later at greater detail. So, vector spaces are quite natural, in abundance. We have always used them, and now it is the time that we see them in the light of a formal structure. Now, why we need to introduce a formal structure? For example, an abelian group, a vector space, a field, etc. Because many spatial situations can be put under one umbrella, and if we understand these structures well, if we understand what kind of properties are true for these structures, then you do not have to consider these examples ad hoc. As I have said, that they can be seen under one umbrella. So, any property, for example, if it is true for a vector space, then it would be true for all these examples, which are examples of vector spaces. A formal theorem which is true for a vector space would be applicable for all these examples. So, let us now begin with such examples, and I hope that you will be able to get a feel what is the need for introducing an abstract notion called vector spaces. We start with examples of vector spaces. As you can see, Rn and Cn are two basic models for vector spaces over the fields R and C respectively. Well, it is a little difficult to explain at this point of time what we mean by basic models, but this will become clear to you as we proceed. And let me just remind you that Rn and Cn are nothing but the set of all n tuples with real entries and with complex entries respectively. And the base fields are different in these two cases. For Rn, the base field is the field of real numbers denoted by R, and for Cn, the base field is the field of complex numbers denoted by C. So, it is very important that we mention the base field whenever we talk about a vector space, because if the base field changes, then the vector space structure may change, the vector space structure may not exist. Therefore, it is very, very important that we mention the base field first and make it explicit. The second example is a generalization of the first one. So, if you take any field, not R or C or Q or ZP in particular, suppose F is the field and you take F to the power n, which is the Cartesian product of F n copies, then you can define the natural pointwise addition and the natural pointwise scalar multiplication on F to the power n, and F to the power n is a vector space with respect to these operations. So, it is a kind of generalization of R to the power n and C to the power n. There is hardly anything new. The only thing you have to be careful about is that the base field is f in this case. So, whenever the base field is given, then when we are doing the binary operations on f to the power n, we just have to be careful and we have to keep in mind that the rules of the field are followed, and this becomes particularly important when the base field is a finite field. This again will be explained later, because the arithmetic becomes slightly different in case of a finite field. For example, if the finite field is Z2, that means addition modulo 2, then 1 plus 1 would be 2, and if we read 2 modulo 2, then it will be 0. Therefore, one has to be careful when one is working with a finite field. Let us now proceed with some more examples. Now, this is a very, very important one, which we denote by m and then little m little n in suffix over R, which is the collection of all m cross n matrices with real entries. Here again, in order to call it a vector space over the field of real numbers, we surely need two operations. One is addition and another is scalar multiplication. The addition is nothing but the addition of matrices, the usual one, and the scalar multiplication is the scalar multiplication of a matrix by a real number, let us say lambda. And how we do that? We just multiply each entry of the matrix by the real number lambda. With respect to these two operations, it is an easy exercise to check that M, M and R is a vector space over the field of real numbers. Now, we come to the next example, that is Rnx, which denotes the set of all polynomials of degree at most 10 with real coefficients. So, typically a polynomial with real coefficients with degree at most 10 would look like a0 plus a1x plus a2x square and so on, an x to the power n, where a0, a1 and an are n plus 1 real numbers. X stands for the indeterminate, and what is important here is that a polynomial like this is uniquely determined by the n plus 1 tuple a0, a1, a2 etc. an, and this n plus 1 tuple is in Rn plus 1. Now, here what is noteworthy is that it is not just that the polynomial is dependent on these n plus 1 numbers a0, a1 and up to an, but on the n plus 1 tuple a0, a1 and all the way up to an, because the positions of these coefficients do matter, in the sense that if we flip the position of a0 and a1, for example, then we get a different polynomial. Therefore, it is the tuple which determines the polynomial and not just the string of real numbers a0, a1 and so on up to an. Now, we all know how to add two polynomials, the usual addition, and also how to multiply a polynomial by a real number, say lambda, that is also the usual scalar multiplication. And this is again a very interesting vector space with respect to these usual addition and scalar multiplication of polynomials. Now, this is a very important remark which we do not want to explain now, but at least it is a good place where I can tell you that this set of all matrices M cross n matrices over R and R to the power mn. So, R to the power mn means the collection of all mn tuples with real entries are structurally the same, or formally which will be called isomorphic as real vector spaces. Similarly, Rnx, that is the real vector space of polynomials up to degree n, and R to the power n plus 1, that means the collection of all real n plus 1 tuples, they are again structurally the same or isomorphic as real vector spaces. So, you have to wait for the formal definition of isomorphism, but you can sort of make a guess why we call them structurally the same. So, first of all, any M cross n matrix is given by m into n entries, because there are m rows and n columns, therefore, there are m into n entries for each matrix. Question is, can we see these matrices as an mn tuple? So, if we can actually identify this mn matrices and the mn tuples, then we will be able to show that the map through which we identify these two sets will have some speciality, in the sense that those maps will be structure preserving. Similarly, for Rnx, we have already seen that a typical polynomial in Rnx is uniquely determined by an n plus 1 tuple, and therefore, we can again create a map between Rnx and R to the power n plus 1, and again we will be able to see that these maps are somewhat special in the sense that they are structure preserving. Now, this comment is again which will be substantiated later. The examples in the next couple of slides are in some sense not quite similar to the previous ones. We will be able to make it precise after some time. Let us see what we mean by this. Example, let us start with a non-empty set X and a field F. Let f to the power x denote the set of all functions from x to f. Again, we are trying to show that f to the power x is a vector space with respect to the following pointwise operations of functions. What are they? So, f plus g is defined as f plus g of x is equal to f x plus g x, and lambda f is defined as lambda f of x is equal to lambda f x, where lambda is a real number and f and g are functions from x to f, that is f and g are elements in the set f to the power x. Again, it is sort of straightforward to verify that this is indeed a vector space over the field f. Now, here we have something interesting for you. If x is a finite set, for example, suppose that x is the first n integers, say 1 to n, then the vector space f to the power x is similar to some vector space you have already seen. So, can you guess what it is? I just leave it open ended for you. It is not very difficult to guess. The moment you see what a function does, then you should be able to make identification of this f to the power x with something that we have discussed before. So, it is a quiz for you. If x is not a finite set, then it is indeed different, and the collection of all functions from x to f, loosely speaking, is huge. That is quite a big set. In fact, if you assume that f is also an infinite set, let us say infinite field to be precise, so f to the power x could be really big. Let us see the next example. Now, we have R x, and that denotes the collection of all polynomials. So, we have seen R n x a couple of slides back, which meant the collection of all polynomials with real coefficients whose degree is at most n. But here we have absolutely no restriction on the polynomial, except that the coefficients are coming from R. So, it is the collection of all polynomials, means there is no restriction on degree as well. Here again we define the addition and scalar multiplication in the usual way, and then R x is again a vector space over the field of real numbers, and it is clear that R x contains all these R n x's as subsets for sure. Another example, C01 denotes the collection of all functions from the closed interval 0, 1 to the set of real numbers, such that f is continuous on the closed interval 0, 1. Once again, we can define the pointwise addition and scalar multiplication of functions, and these are the basic theorems in calculus, that if you have two functions f and g which are continuous, then f plus g is continuous, and also lambda f is continuous. Once again, a very nice vector space structure over the field of real numbers, which is not difficult to check. And what is interesting here is that if you imagine that this 0, 1 closed interval is your x, then C01 is definitely a subset of R raised to 0, 1. So, R raised to 0, 1, by that we mean the collection of all functions from 0, 1 to R, whereas here we are not collecting all of them, we are only collecting those which are continuous. Therefore, this is a subset of R to the power 0, 1. But still we will see that it is quite a big set, it is quite a big vector space. And if you recall, I made a comment that these vector spaces are somewhat different from the previous ones. In fact, at this point I can only tell you this much, that these will be examples of infinite dimensional vector spaces. Now, a theorem which helps you understand the vector space structure better. So, let V be a vector space over a field F. You can see two zeros, one in boldface, one in the regular font, and they are supposed to mean the additive identities of V and F respectively. You remember V is a vector space, therefore V plus is an abelian group, F is a field, therefore F plus is an abelian group. and therefore you do have additive identities. Just to distinguish between them, we are using this bold face and the normal one. Now you have some propositions. So, 0 dot x is 0 for all x in V. So, in the first one, the 0 on the left hand side is 0 coming from F, whereas the 0 on the right hand side is the 0 coming from V. Now, minus 1 in the second one is the additive inverse of 1, whereas minus x on the right hand side of 2 is the additive inverse of x in V. So, you have to remember that you are playing with structures on two sets, one is V, another is F. The structure you have on V is an abelian group structure, and the binary operation is plus, and you also have a scalar multiplication with respect to F on V, whereas on the field F you have two structures, one addition and one multiplication, with respect to which F is a field. The third is alpha dot 0 is 0. Once again, the 0 on the left hand side is the additive identity of the vector space, whereas the 0 on the right hand side is the additive identity of the field. If alpha x is 0, where alpha is a scalar, that means an element in the field F, and x is a vector, that means in V, then either alpha is 0 in F or x is the 0 vector. Proof is straightforward. You just have to keep the abelian group structures in mind. So, 0 in field can be written as 0 plus 0, and then you apply the distributive property which shows that 0 dot x is the 0 vector. Same again for 2, it is the distributive property which is being used. Once again you can see the distributive property being used in 3, and the fourth one, this is where you are using the field structure in full force, in the sense that if alpha is not 0 in F, since F minus 0 dot is an abelian group, therefore alpha has to have a multiplicative inverse, which is denoted by alpha to the power minus 1, which is the multiplicative inverse of alpha that exists in F. Now, starting with alpha x equal to 0, if you apply alpha to the power minus 1 on both sides, then that leads to alpha inverse alpha dot x, but alpha inverse alpha is 1, and therefore you can show that x is equal to 0. This proves the theorem. We have come to the end of module 1 of chapter 2. We have discussed definitions of fields, vector spaces, and we talked about quite a few examples. And now we will be discussing in subsequent modules structures of vector spaces, in the sense we will be introducing subspaces, we will see some specific subspaces of Rn and Cn, and we will be able to relate subspaces with solutions of systems of equations.